We are going to be talking about the Heisenberg's uncertainty principle. This concept refers to that it's not possible to know both the position and the velocity of a moving particle at the same time. How does that relate to the chemistry material that we have been talking about in class? Well, first of all, electrons and the atoms and the neutrons could be considered components of an atom that have mass. And we also know that some of these components may be traveling at extremely high speeds. So if you really would like to understand their behavior, we need sometimes to predict where they are going to be found. As we reviewed in lectures before, the Heisenberg uncertainty principle refers that it's all possible to know both the speed and the location of a given particle. The expression that it takes into place is an inequality expressed as delta x times the mass of the species or the particle times the uncertainty in the velocity, which has to be equal or greater than h, Planck's constant, and divided by 4 pi. And the bottom line here is the more accurately we know the speed of an electron, the less accurately we will know the position, and vice versa. So we can imagine then in the depiction of an 1s orbital that we have here, we cannot really know the position well enough because this electron is traveling extremely fast around the nucleus of this particular atom. Therefore, we use only a probability prediction profile or probability orbital as described here. We will apply this concept to a problem from chapter 7. An alpha particle, which is really helium 2+, an ion that resulted from the loss of 2 electrons from helium, has a mass of 6.6 times 10 to the minus 24 grams, and usually it's emitted when radium isotope is decaying. This alpha particle travels at extremely high speeds, 3.4 plus minus 0.1, 10 to the 7 miles per hour. So the problem that we have here is relates to what is the uncertainty in the position of this alpha particle knowing the speed. So please take a couple of minutes to think about this problem, propose a solution, try to solve the problem, and after that let's compare our solutions. To solve the problem, the first thing is we're going to be using the Heisenberg's expression. For that, we will need to convert the mass to kilograms and the velocity to miles per second. And then we're going to solve for delta x, which will be given in meters. The Heisenberg's expression says that delta x times the mass times delta v is going to be greater or equal to the Planck's constant h divided by 4 pi. And since we are interested in knowing delta x, we're going to solve for that, and delta x is going to be then greater or equal to h times 4 pi divided by m over delta v. Now, this expression then, we have all the values, all the information that was given to us. So what we say then is that, and we're going to replace those values, it's going to be that h, the Planck's constant, is 6.626 times 10 to the minus 34. We keep an eye on the dimensions, joule second. We have 4 pi. And then we are going to divide this expression as well by the mass, which is given as 6.6 times 10 to the minus 24 grams. And also we are going to divide that by the speed, which is given in miles per hour, 0.1 times 10 to the 7 miles per hour. What we need to do next then is use different conversion factors so that we can cancel out the different dimensions. So we are going to include then that 1 kilogram square meter over square second is equal to 1 joule. We are going to include as well that 10 to the third grams equals 1 kilogram. And we want to include that 0.62 miles. I'm going to put the dimensions here for now, equals 1 kilometer. And I'm going to keep adding some of the dimensions down below here, just to keep track of that. 1 kilometer equals 10 to the third meters. And lastly, 3,600 seconds equals 1 hour. So we are going to cross out the dimensions just to make sure we have at the end something that is going to be given in meters. So we have here hours, canceling hours, miles canceling miles, kilometers canceling kilometers. We have square meters canceling meters. We have second, 1 second here. We also have second canceling 1 second. Joules canceling 1 joule. And we have grams canceling grams, kilograms canceling kilograms. The only dimension left is then meters. So if we do the calculations using any calculator, the number that you should be getting should be 1.78 times 10 to the minus 14 meters. And as we can imagine then, in this particular problem, we are talking about a high energy particle that has basically an extremely high velocity. The velocity is really the velocity is so high, and that means that the position of this is going to be really, really well defined. 10 to the minus 14 meters is much smaller than any atomic dimension that we have. In fact, we can use that to target specifically very well defined positions in the nucleus. And this is the answer to this problem.